Hey, welcome to The Explainer. Today, we're going to crack the code of, well, everything. We're diving deep into chemistry, the science that explains the air you're breathing right now, the phone in your hand, and pretty much the entire universe.
Now, I know that sounds like the setup to a really weird joke, right? But the answer is actually kind of profound. It's this incredible connection that links literally everything, everywhere.
Yep, that's it. They're all made of matter, and they all have to play by the same set of rules, the rules of chemistry. So if you really want to understand the world around you, you've got to understand its instruction manual.
All right, so what is chemistry? I mean, it's the study of everything you can touch, see, and smell. To really crack this code, we have to start right at the beginning.
So here's the official definition. Chemistry is the scientific study of matter, basically anything that has mass and takes up space, and all the changes it can go through. Put simply, chemistry is the study of stuff. What's it made of? What can it do? And how can it turn into, well, other stuff? It's really the ultimate science of transformation.
Okay, Section 2, the world's building blocks. From the infinitely small to the things we see every day. And here's what's so wild. All the crazy variety of stuff in the universe, it isn't made from a million different ingredients. Nope, it's all built from just a handful of fundamental pieces. So let's start with the absolute smallest piece, the foundation of everything, the atom. Think of it like the ultimate Lego brick. It's the smallest possible unit of any substance. And when I say small, I mean small. A single strand of your hair is about 1 million carbon atoms wide. Just wow. Everything is built from these tiny, tiny bricks.
And if you look inside one of these Lego bricks, what do you find? It's surprisingly simple. Just 3 little particles. Protons, which have a positive charge, neutrons, which are, neutral, and electrons with their negative charge. But here's the magic. The way these are arranged changes everything. The number of protons tells you exactly what element you're looking at. And those little electrons zipping around on the outside, they're the ones that decide how it's going to interact and bond with other atoms. That's the secret sauce for every chemical reaction.
So, what happens when you get a whole bunch of the exact same type of atom all together in one place? Well, that's when you get an element.
An element is a pure substance made of only one kind of atom, atoms that all have the same number of protons. For example, a bar of pure gold, that's just a giant pile of gold atoms and nothing else. The same goes for the oxygen we breathe. These elements are like the alphabet of the universe, and you can find them all laid out nice and neat on the periodic table.
Okay, so we have our atomic letters. Now let's see what happens when they start forming words. That's where molecules and compounds come in. A molecule is just 2 or more atoms bonded together. Easy enough, right? They can be the same, like the oxygen we breathe, which is 2 oxygen atoms stuck together, that's O2. But if you bond atoms of different elements, like 2 hydrogen atoms and 1 oxygen atom, you get a compound. In this case, H2O, or water. So here's the takeaway. All compounds are molecules, but not every single molecule is a compound. A little tricky, but it's a super important difference.
All right, next up, the states of matter. This is all about how energy organizes those building blocks we just talked about. We know what stuff is made of, but now let's look at the different shapes, or states, it can take. And really, it all just comes down to energy. Let's start with the lowest energy state, a solid. In a solid, all those particles are packed together super tightly in a neat, organized structure. They're kind of just vibrating in place, like they're stuck in traffic. They can't really go anywhere, which is why a solid thing, like your desk, holds its shape.
But what happens when you add a little energy? Say, you turn up the heat. Well, those particles start to loosen up. They break out of that rigid formation and can start sliding past each other. The traffic starts flowing. That's a liquid. It'll take the shape of whatever you pour it into, but its volume stays the same.
Okay, now let's crank up the energy even more. With enough juice, those particles completely break free from each other. They're just zipping around randomly at super high speeds, bouncing all over the place. That's a gas. And a gas will just keep expanding to fill any container you put it in, no matter how big.
And then there's the final state. What if you pump in a ridiculous amount of energy? Well, you can actually tear the electrons right off the atoms. This creates this super hot, electrically charged soup of particles called plasma. You might think, I've never seen plasma, but it's actually the most common state of matter in the whole universe. It's the stuff that stars are made of.
All right, Section 4, physical versus chemical changes. Is it just mixed up, or is it something completely new? So we've got our building blocks, we know the different states they can be in, but now for the really cool part. The most exciting part of chemistry is when stuff changes. And there are two big ways that can happen.
Here's the deal. There are physical changes and there are chemical changes. The big question you always have to ask is this: did I make a brand new substance? A physical change just messes with the appearance. No new substance is formed. But a chemical change? That's a whole different ballgame. That's when you actually create something totally new, with brand new properties.
Let's look at some examples to make this crystal clear. A physical change would be like melting ice. Sure, it goes from solid to liquid, but it's still H2O, right? It's still water. Or breaking glass. It's just smaller pieces of the same glass. But a chemical change, think about rusting iron. The iron combines with oxygen from the air to make iron oxide, which is a totally new thing we call rust. Or burning wood, you can't unburn it. The wood is gone. It's turned into ash, smoke, and gases. You've made new stuff. That's the difference.
Okay, so our next section is about the golden rule of chemistry, the one law that governs every single reaction. Through all these changes we've talked about, from ice melting on your counter to a star exploding millions of light years away, there is one single, unbreakable rule that everything has to follow. And here it is. Matter cannot be created or destroyed in a chemical reaction. This is known as the law of conservation of mass. It's a fancy way of saying you can't just make atoms magically appear, and you can't make them disappear either. All you can possibly do is reshuffle the ones you started with.
This basically means that mass in always equals mass out. The stuff you start with in a reaction, we call those the reactants, has a certain total weight, and the stuff you end up with, the products, has to have the exact same total weight. It's a perfect balancing act, every single time, no exceptions.
So really, chemistry is just the ultimate act of recycling. Nothing is ever truly lost. It's just rearranged. It's kind of mind-blowing when you think about it. The very same atoms that were part of a dinosaur millions of years ago might be in the air you're breathing right now, or even a part of you. They've just been recycled and reshuffled over and over for eons.
And that kind of leaves us with a pretty big question, doesn't it? If all matter is just a rearrangement of the same basic elements, what new materials are we on the verge of creating? We know the Lego bricks, we know the rules for how they snap together. The only thing limiting us now is our own creativity. So what's next?